Okay, a question about energy and power sources. First question, describe the energy transfers that take place in the power station. Well, here's the power station. 4 marks. Okay. Well, it all starts here in the reactor. You have your radioactive material here, and that undergoes nuclear fission. So, what's the energy transfer taking place there? Well, you're going from nuclear energy or nuclear potential energy, that's in the uranium or whatever it is, and when it undergoes fission, the products of fission fly away very fast. So that's a conversion of nuclear potential energy into kinetic energy of the fission products. Okay? 1 mark. Right, what happens next? Those fission products fly into the surrounding coolant, collide with it, and heat it up. So in this coolant here, you have a conversion of kinetic energy of the products of fission into thermal energy of the coolant. Okay, 2 marks. Right. So this little thing whirs round and pushes the coolant round. So the hot coolant goes into this region and heats up water in the boiler. So there's going to be water in the boiler here, okay? And it boils the water. It's above 100, heats it to above 100 degrees C. So it turns it into steam. Now, I suppose you could say you've got thermal energy in the coolant being transferred to thermal energy in the water in the boiler, but that's thermal to thermal. That's just heat transfer by conduction. So I'm not sure if I'd give you a mark for that or not. However, let's keep going. So you have thermal energy in the water in the boiler. That creates this steam which is under high pressure, and the steam forces its way through the turbine. Okay, so you've actually got thermal energy in the water being converted into kinetic energy of the steam. Okay, because the steam goes through here at quite high speed and pushes the turbine round. So that could be your 3rd mark. Thermal energy of the water or thermal energy of the steam to kinetic energy of the steam. Okay. Then, like I said, the steam forces its way through the turbine, causing the turbine to rotate. So again, you've got kinetic energy of the steam into kinetic energy of the turbine. So that's kinetic to kinetic. I'm not sure if they'd give you a mark or not, because it's the same type of energy, but no harm in mentioning it. Okay, so you have kinetic energy of the turbine. That's directly connected to the generator, so you get kinetic energy of the generator because it's spinning with the turbine. Okay. Then in the generator, the kinetic energy of the generator is converted into electrical energy because that's what generators do. 4 marks. Okay, so you've got your 4 marks by this point, and the electrical energy, well, that just goes into the city or town or wherever. Anything else you could say? You've definitely got 4 marks at this point. Could you say a bit more? Possibly. They've shown a condenser here in the question, so you could say kinetic energy of the steam as it passes through the turbine. It's cooled, so you could say no, you wouldn't want to say kinetic energy to something else there because it slows down having converted its kinetic energy into kinetic energy of the turbine. You could say thermal energy of the steam into thermal energy in the condenser, maybe. If you want to say a bit extra, because the condenser is cooling the steam, it's turning back into water here. Okay, that's more than enough to get you 4 marks. Okay, right, next question. Which of these types of power station uses gravitational potential energy to generate electricity? Wind farm, geothermal power station, hydroelectric power station, or coal-fired power station? Okay, gravitational potential energy, it's the hydroelectric power station, because the way they work is you have a big dam, okay? All right, and a lake here or something, or maybe it started as a river before they put the dam there. Now they've turned it into a big lake full of water. Okay, so loads of water there. There's the dam, and they let the water through these tubes at a controlled rate, and the water comes out here. Okay, and keeps flowing away. And you have turbines in here somewhere, so they can convert the gravitational potential energy of the water into kinetic energy of the turbine, and then, like here, into electrical energy with a generator. The point is that a hydroelectric power station uses gravitational potential energy. If they close these gates here, you've just got a whole bunch of water sitting there waiting. It's not moving. But it's a huge mass of water, and it's higher than the point at which it flows out. So you have a mass that's raised to a height, okay? So it contains a lot of gravitational potential energy, and that's what's released when they open the gates and let the water through to turn the turbine. Okay. Right, which of these types of power station transfers thermal energy to generate electricity? A coal-fired power station, a solar farm, a hydroelectric power station, or a wind farm? Okay, well, it's not the wind farm. That does not use thermal energy. It uses kinetic energy of the wind. Hydroelectric power station. No, that's not transferring thermal energy, transferring gravitational potential energy like we talked about. A solar farm, okay, you could get caught up here. It's not a solar farm, okay? The question's asking which type of power station transfers thermal energy to generate electricity. It's tempting to think of sunlight as thermal energy, okay? But technically it's not. Sunlight is electromagnetic radiation, okay? So it's electromagnetic energy. I know the sun is hot and it warms you up when it lands on you, but thermal energy is the physical vibration and movement of particles, okay? And the light that comes from the sun, it's made of photons, and these photons are not vibrating, okay? There's no physical movement. Photons don't have a mass, okay? So don't fall into that trap. It's the coal-fired power station that transfers thermal energy to generate electricity. You burn the coal, it gets hot, and that's how you boil the water here. Okay. Right. Okay, a power station needs an input of 188 joules per second to operate a 60-watt lamp. Okay, so we've got this. That's not very good, but it's good enough. This Sankey diagram, okay, which looks something like this. Okay, neaten that up a bit. That's fine. Okay, so 188 joules of input into the power station. and you have a 1.5 joule useful energy output in the lamp there, okay? So that bit is the lamp. This bit is are the transmission lines, and this is the power station. Okay. Right, which is the main form of energy wasted in the lamp? Okay, so this line separates the lamp. So 1.5 useful joules of output from the lamp, but there's 58.5 joules of something else here. Well, what do you know about incandescent light bulbs or lamps? Okay. The filament is very inefficient because it's designed to create light energy, 1.5 joules of light energy, electromagnetic energy, like we were just talking about. But you should know that filament lamps are very inefficient because they generate a very large amount of heat, thermal energy, okay? So that's light, EM, electromagnetic energy, is useful, and the rest is all thermal energy. Okay. Oh, right, there are 4 options: sound, thermal, electrical, or light. It's thermal. Right, next question. State the relationship between efficiency, useful energy output, and total energy input. You've just got to know the definition and the equation of efficiency off by heart, okay? So if you don't know it, learn it now. It's this: the efficiency is useful energy output divided by total energy input. Okay? So that's it. Like I say, you need to know that equation, so learn it now. Right, calculate the overall efficiency from power station input to lamp. So 188 joules input in the power station to the lamp, 1.5 useful joules of light energy output. Okay, well, just stick it into the equation. So the efficiency is useful energy output, 1.5 joules, 1.5, divided by total energy input, 188. Stick that in your calculator and you get 0.00797872 something something something. Okay. You're not going to leave it like that. Choose a sensible number of decimal places. I think stopping there is sensible, so that's equal to 0.00. That 9 pushes, that 7 pushes that 9 up to 0, and that whole thing up to 80. Okay, 80. So that's 4 decimal places. Okay, and that's it. That's the efficiency. Right, you can leave it like that, but often you have to give efficiency as a percentage. So my advice in an exam is to hedge your bets. Give both answers, then you definitely get the marks, okay? To convert that into a percentage, you just multiply by 100. So that means moving the decimal point 2 places in that direction. So that's 0.80, 0.80%. Okay. That doesn't have units because it's energy divided by energy. Okay, so they cancel out, no units. But if you're going to write it as a percentage, you have to write the percent. Okay. And finally, you can write this as a percentage if you want, okay? You can write it as efficiency is equal to useful energy output, okay, divided by total energy input times 100. And now if you multiply it by 100, then it's a percentage. So, ouch, that is loud. Either of those is okay. There we go. Thank you for watching. I hope you found this video helpful. If you did, please click the like button, and it would be a massive help if you could subscribe. It would also be amazing if you could support me on Patreon. All the papers and everything are on my website, drjem.com, and I'm also on social media. Thank you.